All right. So thanks everybody for coming and welcome to another session of Probability and Analysis webinar. We're really pleased today to have Rocco Servedio from Columbia with us, who, among many other things, has made a number of fundamental contributions to the analysis of Boolean functions. And we're really happy to have him here to discuss one of those today. So with that, take it away.
Super. Thanks very much for the introduction, Joe. And thanks to Joe and Irina and everybody for inviting me to talk in this seminar. So I'll be talking about convex influences and a quantitative Gaussian correlation inequality. This is joint work with Anindya Day at UPenn and Shivam Nadampally, who's at Columbia, and I think also on this Zoom call. So the goal for the talk, let's see if I can advance slides, good. I guess I have three goals for the talk. The first one is I want to lead off with kind of a teaser, what I think is this intriguing analogy between monotone Boolean functions, so functions over the discrete 0, 1 Boolean hypercube that are monotone increasing, an analogy between these objects and symmetric convex sets in Euclidean space. In particular, we think of having a standard Gaussian distribution over Euclidean space. So I'll try to hopefully sell you on the fact that there is some interesting phenomenon here. If you kind of know something about what happens in the monotone Boolean case, you can often make a very good guess as to what will happen in the symmetric convex Gaussian setting. This analogy will lead us sort of very naturally, we won't kind of have a choice, to formulate a conjectured quantitative version of the Gaussian correlation inequality. And probably the bulk of the talk, I'll be telling you about how we prove this quantitative version of the Gaussian correlation inequality. Then once we have this quantitative Gaussian correlation inequality in hand, we'll again be sort of led by the nose by looking at it and comparing it with an analogous statement over the Boolean setting. We'll be led naturally to this new notion of influences for symmetric convex sets. So it'll sort of motivate us to define and explore a new notion, which is what we call convex influences. And if I have a minute at the end, I'll tell you maybe a little bit about an algorithmic application of this new notion. So that's the high-level plan for the talk. Please ask any questions as we go on throughout. Let's get into it. Looks like it's a little slow to advance. Whoops, now it's going to advance twice. So yeah, so I want to start off by telling you a little bit about this analogy between monotone Boolean functions and symmetric convex sets. So just to give you a sense of sort of the graphic design of the talk. Oh, I should also thank Shivam. Almost all of these slides are almost entirely Shivam's work. So if you have criticisms about the slides, you can deliver those to Shivam, but really I want to thank him for doing the bulk of the work in setting up the slides. Yeah, so kind of just to give you a sort of an explanation of the pictures I'll be drawing. This is my crude representation of the Boolean hypercube on the left. We would think of the all ones input, the vector 1 to the n up here on top, and the all zeros input, the vector 0 to the n down here on the bottom. And so this is kind of a cartoon of a monotone Boolean function. We all know what these are. They're 0, 1 valued functions. As you walk up the hypercube, you'll never change the value of the function from 1 to 0. It's sort of monotone increasing in each of the n coordinates. On the other side of the slide, we have a picture of a symmetric convex set. I think this actually should be a hexagon, an even number of sides instead of a pentagon to really be symmetric. But the idea is clear, right? A symmetric body, just symmetric around the origin. If x is in the set, then minus x is in the set, and it's convex. So of course it contains the origin. So why do I say there's some kind of analogy between these objects? Well, maybe a very superficial way to see the analogy at first is imagine you're at some point in the Boolean cube and you want to walk up to that all ones input. Well, you're walking, you're going through the 0 part of the function, then you cross the boundary into the 1 part of the function and you stay in the 1 region as you walk up to the all ones input, okay? On the other hand, something similar happens if we think about Rn. I start off someplace in Rn, maybe I'm outside my object. I walk in toward the origin now. So sort of 0 to the n is the analog of 1 to the n in the left-hand side of the picture. And eventually I cross into the object and then I stay in there as I go in all the way to the origin. Okay, this probably doesn't seem too compelling or striking, but I claim that actually there's a much deeper range of correspondences between these two settings. And the next slide hopefully will convince you of that. So let's see what we get. A little slow to advance. Okay. Yeah, so here's a slide with probably too much information about monotone Boolean functions, some of the things we know about them. What do we know? Well, one thing we know is they have very nice analytic structure. There are these well-understood bounds on Fourier concentration. If we think of like a orthogonal polynomial representation of a monotone Boolean function, we know that almost all the weight in this Fourier representation is going to be on relatively low degree basis functions up to degree root n. And this leads us to learning algorithms, in particular algorithms if you want to learn an unknown monotone Boolean function to say accuracy 99% from uniform random examples. We get that from the analytic structure. We also have more combinatorial flavored results, things like this Kruskal-Katona theorem, what I'm referring to as density increment results. What does this mean? It's just, I don't have a picture, but basically, if you just think about looking at a weight level, a horizontal slice of the Boolean hypercube, and you sort of walk up the hypercube slice by slice, you can ask, how dense is my monotone function? What fraction of each slice is contained in the monotone function, contained in the set of 1 inputs? And the Kruskal-Katona theorem tells us how this fraction, this density increases as we walk up the Boolean function. Okay, so that's another kind of result we know about monotone Boolean functions. This can be leveraged to get weak learning results if we want to learn in polynomial time, but just want to learn to some small advantage over random guessing. And I'll talk much more about correlation inequalities in a few slides, so let me not mention them right now. So this is some of the things we know about monotone Boolean functions. For no good reason that I can really understand, it turns out that we have entirely analogous results for symmetric convex sets, when again we think of Rn as endowed with the Gaussian distribution. So the Hermite polynomials, I'll talk much more about this throughout the talk, are sort of analogous to the Fourier basis functions for the Boolean cube. We have Hermite concentration, very much like the Fourier concentration, again at degree root n. And again, this gives us a strong learning algorithm. In recent work, and I think things like this were kind of implicitly known for quite some time, you can establish a density increment result, a Kruskal-Katona analog for symmetric convex sets. Now what you should think of is, instead of walking up levels of the Boolean hypercube and looking at what fraction of the weight level of the Boolean hypercube is contained in your monotone function, think of like a spherical shell around the origin. And as we sort of contract that shell, we make it smaller and smaller going in, you ask what fraction of this spherical shell is covered by or is contained in your symmetric convex body. And it turns out that really, really closely analogous quantitative results to Kruskal-Katona can be established for this symmetric convex setting. And again, this then gives rise to weak learning results, kind of analogous to the results that are known in the Boolean setting. But I think maybe the problem or the question or the sort of branch where this correspondence is the most interesting and maybe the most surprising in some sense, if you know a little bit about the proofs, is this last one having to do with correlation inequalities. So I'm going to talk a little bit now about this analogy, the way it plays out in terms of correlation inequalities in these two settings. Okay, what is a correlation inequality? It's just, when I say correlation inequality, I basically mean an inequality which says, we've got some collection of functions we're interested in, this calligraphic f, we've got some domain and some underlying distribution over the domain. A correlation inequality is just a theorem which tells us that any two functions in that family have non-negative correlation with each other. They can't be anti-correlated. So the simplest version of this is, I guess it's Chebyshev's, what do they call it? Chebyshev's order inequality or something. It says if you have two lists of real numbers and you want to like take the inner product, you should sort both the lists. And that's sort of the biggest way that you'll get the, that's the way to maximize the result of the inner product. These statements are much more interesting when we think about high dimensional correlation inequalities. They come up in a range of areas, and probably the simplest one is for monotone Boolean functions over the discrete hypercube, the so-called Harris-Kleitman inequality. So let me remind you of this if you haven't seen it recently. It's really a very clean, nice statement. It just says that if you have any two monotone Boolean functions, they cannot be anti-correlated. So the expectation of f times g has to be at least the expectation of f times the expectation of g. Okay, if you want to think of it in terms of a picture, if the pink monotone Boolean function covers a third of the Boolean hypercube, we think of it as like, again, a 0, 1 valued function or a subset equivalently of the hypercube. And the blue Boolean function is another monotone function, which covers half the hypercube. Then the purple area, the intersection region where they're both true, has to be at least 1/6 of the hypercube. Okay, so very, very simple correlation inequality. We'll see its proof in a single slide with lots of room to spare in just a minute or two. Okay, another example, if you have this analogy in mind, and I say, hey, Gaussian setting, what should happen? You would kind of automatically be led to conjecture the Gaussian correlation, what was the Gaussian correlation conjecture for a long time and eventually became the Gaussian correlation theorem or the Gaussian correlation inequality. This just says the exact analogous thing for symmetric convex sets with respect to the Gaussian distribution. It says if you have any two symmetric convex sets, they cannot be anti-correlated with respect to the, the centered Gaussian distribution, the standard Gaussian. I want to emphasize that while the Harris-Kleitman theorem, again, is really trivial, it has a one paragraph proof, really one line proof by induction. Royen's inequality, the Gaussian correlation theorem, is far from trivial. It was open for quite a few decades. There's a nice quant article about kind of the history of how it was open and how it was eventually solved. So even though we have a very similar phenomenon, the statements are closely analogous, the proofs don't seem to really align with each other at all. There isn't a way to sort of look at one setting and get the other setting. Okay, and just a picture of the Gaussian correlation inequality. It's the exact same kind of thing as before. If the Gaussian measure of the blue strip is 1/2 and the Gaussian measure of the pink ellipse is 1/3, then what the theorem says is that the Gaussian measure of the purple intersection region is at least 1/6. Okay, so really very closely analogous to what happened in the Boolean setting. Okay, so what we've seen so far is this Harris-Kleitman inequality, this Gaussian correlation inequality. They're both qualitative inequalities. What I mean by that is they sort of tell us, hey, you have non-negative correlation. We have this greater than or equal to 0, but they don't tell us sort of quantitatively something about how strong that correlation is. It's easy to see that, in kind of the worst case, the correlation could be 0, but maybe if I know something about f and g and how they relate to each other, I'll be able to give some kind of quantitative version of these inequalities. Right? I sort of look at f, I look at g, I say, oh, based on how they relate to each other, I can come up with some kind of quantitative statement. So indeed, that can be done. And to do that, let's look back at the Harris-Kleitman theorem. We'll sort of see its proof in the next slide. And by looking at its proof, we'll be led to kind of conjecture what type of quantity a quantitative version of Harris-Kleitman might be expressed in terms of. So again, this is just the statement of Harris-Kleitman. It says you have two monotone functions. They cannot be anti-correlated. There has to be non-negative correlation between them. The way we're going to prove it in the next slide is just by really the simplest approach you would think of. We're going to break down each of these functions into sub-functions. So we'll take one coordinate, say the nth coordinate, and we think of the function f as corresponding to two sub-functions. F0 is what I get if I set the last bit to 0. And f1 is what I get if I set the last bit to 1. So just a little bit of notation for how we would decompose f based on the value of its last coordinate. We have the same notation for g, g0 and g1. Okay. So this is the entire proof of Harris-Kleitman. Given this definition of f, that we break it down into the f0 part and the f1 part, and likewise for g, it's just a trivial calculation to verify that the left-hand side, the quantity we're interested in, the thing that we want to show is non-negative, can be expressed in, in this form on the right-hand side. Okay, this is just completely straightforward to verify. And now given this, it's a proof by induction where we're 30 seconds from being done. F0 and G0 are n-1 variable functions. Since f and g are both monotone, F0 and G0 are both trivially monotone. So by induction, we know that this numerator, this purple quantity, is non-negative. So that's good. Same thing for F1 and G1, they're monotone. So this is again, by induction, non-negative. It's the n-1 variable version of the statement. And finally, we're just left with this last part. What can we say about it? Well, again, I keep saying the same thing. F is monotone. And as a consequence of the fact that f is monotone, if I look at this function, f1 minus f0, it is pointwise non-negative. This is the definition of being monotone. Is things don't decrease when I flip that last bit from a 0 to a 1. So this expectation of this pointwise non-negative function is certainly non-negative. Hence, this is non-negative. Same thing for the other half, and we've proved Harris-Kleitman. Very, very simple proof. Okay. And now, kind of foreshadowing a little bit, let's look at this quantity. I think I may be off by a factor of 2 here or something, but this highlighted purple quantity, this expectation of the difference of the two functions, f1 minus f0 over 2, I think up to a factor of 2, it's exactly this probability, right? Because again, when we flip that last bit, it only ever changes the value of the function from 0 to 1. It's the probability that, if you take a uniform random input and you flip the last coordinate, the value of the function changes. Okay, now this is a quantity that we're probably familiar with. This is the so-called influence of that last coordinate on the Boolean function f. Again, that's just the probability. You take a uniform random input, flip the last coordinate. What is the overall probability that the function's value changes? So this is a central notion in the analysis of Boolean functions, studied by many people, useful in a wide range of contexts. Okay. Okay, so what's happened? We proved Harris-Kleitman. That was great. Now let's think about how could we have some kind of robust version of it or quantitative version of it. Well, let's look at the proof that we just saw. It's written down here. it's pretty easy to see that the only way we will actually have equality, the only way that the expression on the right-hand side could be 0 is if for each coordinate, remember, we kind of peeled off this nth coordinate, but we could have peeled off any of the n coordinates and sort of done the inductive proof in any order. The only way that we'll get 0 on the right-hand side is if this quantity is 0 and this quantity is 0. In other words, if either the influence, sorry, I'm sorry, I said that completely wrong. If either this quantity is 0 or this quantity is 0 for each coordinate. Okay, you can see that if for each coordinate, one of these two things we're multiplying together is 0, then we will get 0 on the right-hand side from this last contribution at least. And you can show without too much trouble that this is an if and only if. Okay, so you're going to have equality in Harris-Gleitman if and only if for each coordinate, either the influence of each coordinate I, either the influence of coordinate I and F is 0 or the influence of coordinate I and G is 0. In other words, if that product turns out to be 0. Okay. So this suggests very strongly that, maybe you could come up with some kind of quantitative version in terms of this quantity, this sort of inner product of the influence vectors. If it is 0, then you're going to have equality in Harris-Gleitman, and the opposite is true. If it's not 0, you're not going to have equality in Harris-Gleitman. So it seems like this might be the right quantity to be looking at if we want a quantitative statement more generally. And that's a very rough intuition, but it turns out to capture the truth of the matter. So Talleyrand, back in, I guess, the mid-90s, gave a quantitative version of Harris-Gleitman. He proved that for any monotone Boolean function, this slightly funny-looking function, basically x over log 1 over x, if we feed into it this inner product of the influence vectors, that gives us a quantitative version of Harris-Gleitman. You can show that this is actually tied up to constants for various examples. It's not an obvious proof at all. You have to do sort of Fourier analysis where you're looking at the level 2 weights of these monotone Boolean functions. So it gives us what we want. It's I would say definitely non-trivial how to establish it, and it's a useful and kind of, I think, independently interesting kind of theorem to have this sort of quantitative statement. So at this point, you can probably guess where we're going, right? We sort of started off talking about qualitative correlation inequalities. So Harris and Gleitman over on the left, we have that the correlation between monotone functions is non-negative. Royen's theorem over in the Gaussian setting on the right, that for symmetric convex sets, under the Gaussian distribution, the correlation is non-negative. And you can tell where this is going to go, right? What about quantitative versions of these statements? We have Talleyrand's statement in the monotone Boolean setting, which gives us a quantitative statement. It's natural to ask, can we get an analogous quantitative statement in the Gaussian setting? This might seem frightening because, wow, the Gaussian correlation theorem is a lot harder to prove than the Boolean setting, but it turns out it's doable, and you don't even need to know the proof of the Gaussian correlation theorem to do it. I don't know the proof of the Gaussian correlation theorem. So in India, Shivam and I showed that we get some very analogous looking statement. I want to sort of highlight the similarities and the differences, starting with the differences. First, maybe let me call your attention to the purple stuff. We didn't meet the bar that Talleyrand met. We don't have a function which is quite as good as x over log 1 over x. We have x over log squared 1 over x. And we'll see why we have this, and I'll talk a little bit more about that in a little bit. So that's kind of the difference. The other difference you notice is, oh, I've got these funny things here. What are these? These are these degree 2 Hermite coefficients of the function k and the function L. But sort of the propaganda part of this talk is I want to convince you that we shouldn't think of this as being different at all. I'd like to sort of, the last thing I'll be arguing in the talk is that we should be thinking of these degree 2 Hermite coefficients as really being, I think, a good and interesting and a productive to think about notion of influences for symmetric convex sets over Gaussian space. Okay, so that'll be the haranguing part of the talk at the end, where I'm like, this is a good notion of influence for symmetric convex sets under the Gaussian distribution, but we'll get there in a little bit. Okay, so for the next part, are there any questions at this point? The eerie thing on Zoom where you don't know. But anyway, yeah, break in with questions at any point if anybody has questions. For the next portion of the talk, what I would like to do is give you an overview of why this quantitative Gaussian correlation inequality is true, how we're able to show it. Okay, so just reminding you of what it says, it again gives us this quantitative lower bound on the correlation between two symmetric convex sets, and it's done in terms of these degree 2 Hermite coefficients of the sets or the functions k and L. And later on I'll propagandize you that we should think of these as influences, but for now it's just a statement about this Hermite decomposition of these sets. Okay, so I'll give you the high-level proof strategy, and then we'll go through the 3 stages. It's essentially an interpolation argument. We're going to see how by working with the Gaussian noise operator, we are able to view the expectation of k times L as sort of taking this noise parameter to be 1, and the expectation of k times the expectation of L is the expectation of as a corresponding quantity where the noise parameter is set to be 0. So it's one of these arguments where you vary a noise parameter, and we sort of the two quantities we care about are the two extreme ends of that. We have this monotonicity of interpolation. So I don't know Royan's proof. I can't explain Royan's proof to you, but if we look at what just the statement of what Royan really proved, it's exactly that he gave us monotonicity of this interpolation. And that turns out to be exactly what we need for our purposes. All we're going to do is a little bit of relatively straightforward Hermite analysis, and then we'll drop down, I guess, a new lemma about extremal power series in a single complex variable. And by combining that new result with sort of this Hermite decomposition view of things and using Ryan's monotonicity of interpolation, we'll get our result. So that's a very high level explanation. I'll flesh out the explanation and what's coming up. Yeah, so I'm gonna have to talk about sort of Hermite representations of these convex sets as the first thing. So this is again the basic order in which we'll go through the argument. I'll give you the basics of harmonic analysis over Gaussian space. Once we've covered what we need from that, I'll talk a little bit about Ryan's proof, this monotonicity of interpolation, and then we'll see the new part, this new complex analysis lemma, and we'll see that it leads us to this sort of, to the theorem statement. And once we have the theorem statement, I'll segue to the very last part of the talk, talking about convex influences. Okay, so let's get into it. We're going to start with the harmonic analysis part. Probably some of you have seen this a million times, and it's going to be super boring. If you've never seen it at all, but you've seen harmonic analysis in other settings, like the Boolean hypercube or something, it's entirely the same thing in spirit, but just kind of a different setting. Okay, but anyway, let's do it. Yeah, so we're thinking about, again, square integrable functions over Gaussian space. We're just going to be thinking about 0, 1 valued functions, these indicator functions of convex sets, symmetric convex sets. So we have an inner product with respect to the standard Gaussian distribution. We have a norm based on that inner product. Everything is nice. Let's look at just the one-dimensional case. In the one-dimensional case, if we're just thinking about functions of a single Gaussian variable, we have this nice orthogonal decomposition. We can express functions as linear combinations of these so-called Hermite polynomials, right? So you just do Gram-Schmidt orthogonalization. You start with the constant 1, you get the function x as your next orthogonal polynomial, x squared minus 1 over root 2, or whatever it is. And going on, we have this nice set of orthogonal, in fact, orthonormal polynomials in a single real variable, which we think of as endowed with the Gaussian distribution. Okay, so that's one-dimensional polynomials. Of course, we're interested in n-dimensional sets, n-dimensional functions, so we just do the natural thing. We take tensor products of these one-dimensional functions. So pretty much for the rest of the talk, when you see alpha, it's going to mean like a vector of n natural numbers, like an index of, you know, these degree 3 in the first variable, degree 5 in the second variable, so on and so forth, just these multi-dimensional basis functions. And indeed, they behave the way you would want them to behave, right? They're going to be a complete orthonormal basis for square integrable n-dimensional functions over Gaussian space. And this gives rise, of course, to the notion of the Hermite expansion, like the Fourier expansion in your favorite domain. We're just going to write f tilde as like the Hermite coefficient, the correlation between the function and the Gaussian basis function. Yeah, so this is going to be what we'll call the Hermite expansion of our functions. Okay, and again, for us, the functions we're going to be interested in are these indicator functions of the symmetric convex sets that we ultimately care about. Okay, yeah, Hermite coefficients, just these f tilde alpha things. Good. So everything happens the way we would want it to happen. We have Parseval's identity, which says that if we're interested in the inner product between two functions, it corresponds to just this inner product between the vectors of the Hermite coefficients. So we've seen this kind of thing before. But also we have, you know, as a special case, the squared norm of a function is just the inner product of its vector of Hermite coefficients with itself. So very, very standard kind of stuff. Good. Last piece of sort of conceptual technology or terminology that we need is this notion of a noise operator. So it's a standard thing, the Gaussian noise operator. What does it do? When we apply the Gaussian noise operator at some noise rate rho or some noise parameter rho to a function f, it means we're taking the average over sort of 1 minus rho noisified scaled versions of f. And we're seeing what that is. So the parameterization may be a little different than what you're used to. It's going to be convenient parameterization for this talk, though. So let's just look at sort of the two ends of the parameter regime. If the noise parameter is 1, that corresponds to, we're just taking f of x with no sort of random Gaussian part mixed in at all. So when the noise parameter is 1, u rho of f is just the same thing as f. It's like an interesting function. On the other hand, if we set the noise parameter to be 0, then x is completely gone away, and all we have is the expected value of f on a random Gaussian input. Okay, so u rho of f, if rho is 0, is just a fixed scalar. It's just the expectation of f. Okay, so sort of two extremes of the of how noise can affect a function. Okay, so why do we care about this noise operator? Well, it interacts very nicely with the Hermite expansion. So in particular, if we have a Hermite basis function, it gets attenuated if we apply noise at rate rho by sort of shrinking it down by this factor of rho to the total degree of the basis function. Okay, so we've seen this kind of thing before, how noise interacts with the orthogonal basis. Excuse me. Okay, that's it. That's all we need to know about sort of Hermite expansions. This is, you know, this from this we'll be able to make the whole thing work. And this is just a recap of what we just said. Okay, now let's talk about Royen's proof a little bit. It's going to be only a little bit because, again, I do not know the proof. Just to remind you of what the inequality says, it says that if you have a symmetric convex set, then the two symmetric convex sets, they cannot be anti-correlated with each other. The expectation of their product, this 0, 1 valued product, minus expectation of the first one times expectation of the second, product of the Gaussian volumes, is non-negative. Okay. Now, in light of this discussion of noise operators that we just talked about, it's natural to think about, you know, re-expressing things in this way. If we look at U1k, again, that means that just we didn't change k. That's just the inner product between k and l. So it's the expectation of kl. On the other hand, if I look at U0k, then I just destroyed k and, you know, it became a constant function. So that's the inner product between the constant function expectation of k and l. So that's, of course, this quantity. So we can see that what we're interested in, Royen's inequality, really rephrasing it this way, says that we have that the inner product when we have noise parameter 1 is at least the inner product when we have noise parameter 0. Okay, just a rephrasing of Royen's inequality. So nothing really happened there. Okay, you know, back in 2014, Royen wants to prove his theorem. What does he have to do? He has to show that the value of this inner product on the left when the noise parameter is 0 is at most the value of this inner product on the right when the noise parameter is 1. Okay, he looks kind of worried, and the reason he's worried is probably because he's worried that something like this might happen. If the, you know, inner product was not a monotone function of rho, it seems kind of complicated. How do you know it's going to end up bigger than it started out? Again, thank you, Shivam, for these great slides. Here's a picture of happy Royen because, you know, the world turns out to work the way he would like it to work. The inner product is monotone in this row. And in fact, that's really what Royen proves. What we think of as Royen's theorem or the Gaussian correlation inequality is this sort of simple consequence of the fact of what his theorem really states, which is that the derivative of this inner product with respect to the noise parameter is non-negative. And of course, we get from this that, you know, U1k inner product with L is at least U0k inner product with L. Okay. So this is what we should think of Royen's theorem as really establishing, monotonicity of this interpolation process. Okay, and that's all we need to know about Royen's theorem too. It's great. Good, so now we're gonna get to the new part. How do we actually prove this quantitative version of the Gaussian correlation inequality? So we're just gonna write things down and see what happens. Again, we're starting with our symmetric convex sets. We would like to give some quantitative lower bound on this this correlation. And again, we're going to write the correlation as U1k inner product with L minus U0k inner product with L. Okay. Let's write these things down. We know that if we apply the noise operator at rate rho to our set k, we get this expression on the left. The, you know, degree alpha Hermite coefficient is attenuated by rho to the alpha. We don't do anything on the right. It's just the Hermite representation of L. We have Parseval's identity, so we can write down an expression for the inner product of the sort of rho noisified version of k with L, and it comes out to just be this expression here, right? It's sort of, you can see what it is. We're interested again in this thing when rho equals 1 minus this thing when rho equals 0. Well, it's easy to see that this thing when rho equals 0, all the terms are going to go away except for the constant term. So that'll just be subtracting off the one constant term. So if we look at that difference, u rho KL minus u zero KL, it's just going to be that sum that we saw in the last slide, except we got rid of the zero term, right? The sum is only over non-zero vectors alpha, sort of these non-trivial basis functions. Okay, well, you look at this and it looks like a power series, right? It's something of the form a1 rho plus a2 rho squared plus a3 rho cubed, so on and so forth, where these AIs correspond to kind of the inner product of the Hermite weight at level 1, level 2, level 3, so on and so forth. Okay, so we have some kind of power series that we're trying to deal with. It's really a one-line argument that by Cauchy-Schwarz and Parseval, we know something about the sum of the magnitudes of the coefficients of this power series. It turns out that it sums to at most 1. This is the so-called length of the power series. And I guess we know something else as well. Since these are symmetric functions, we don't have any odd component when we write down the Hermite representation of either K or L. So things kind of clean up a little bit. The quantity we're interested in, it really is a power series like a2 times rho squared, plus a4 times rho to the 4th, plus a6 times rho to the 6th, so on and so forth. So, okay, it's natural to say, let's clean it up a little bit more. Let's sort of break out the a2 part. Let's replace rho squared by some parameter t. And you sort of are led to, consider this power series, which I'm calling P of t. It doesn't have any constant term. We factored out the a2, so it looks like t plus some coefficient times t squared plus some coefficient times t cubed, so on and so forth. Okay. The question we would like to answer is, how large can we show this power series has to be somewhere on that unit interval? We would like to give a lower bound on the supremum of this power series over the unit interval. Okay, let's look at this question a little bit more generality. So again, I've just got some power series and I know what it looks like. No constant term, starts with t. I know something maybe about the sum of the coefficients in the power series. And I'm going to think about feeding in values of t between 0 and 1, real values. And I'd like to say, there's got to be some point where it's not too tiny. You can kind of notice that point is not going to be right around 0, because at 0, it's going to be 0. But we'd like to argue that, hey, it has to be non-trivially large somewhere. Why would we like to argue this? We'd like to argue this because Royan gave us monotonicity of interpolation. If we can show that it's non-trivially large somewhere, Royan tells us, it's actually at least that large at the right endpoint at t equals 1, which is where we're interested in, right? So that's very useful for us. So here's kind of a clean standalone version of the statement we'd like to answer. We have this power series. It looks like t plus some coefficient times t squared plus some coefficient times t cubed, so on and so forth. We know that first coefficient is 1, and let's say we know it. We're just going to give a name to an upper bound on the sum of all the coefficients. We'll call it m. Okay, don't worry about the 3/2 thing. If m is less than 3/2, it turns out to be super easy to get what we want. We'd like to show a lower bound on how large this power series like this has to be somewhere on the unit interval. And we end up showing that it's at least 1 over log squared n. Okay, and this is exactly the log squared in the denominator we saw in our function before. You might say, oh, you guys should have worked a little harder and proved a better bound, gotten just 1 over log n, but it turns out you can't do that. We can give an example where for this particular question, really, it could be as small as 1 over log squared n. Okay, so I'm not going to prove this theorem, but I'll give you a 2-slide cartoon of the proof, which hopefully will give you a sense of how it would go. Okay, again, we're trying to lower bound the value of a power series that looks like this, somewhere on the unit interval. We kind of know we should be looking away from 0, because it could be, it goes to 0 as t equals 0. So it's natural to break it down and write something like this. We're going to think of it as factoring out a t. So it's t times this 1 plus c2t, c3t squared, so on and so forth. And we'll try to optimize over kind of the right part of the interval. We're not even going to try to sort of get a large value very close to the origin, because of course we can't. Okay. So the rest of the quote unquote proof is captured in this picture. What would we like to do? We'd like to show that this power series, this is the complex plane. We'd like to show this power series is not too tiny, somewhere on the real line between delta and 1. Okay, so we draw a couple of ellipses. We think of that red line segment as a degenerate ellipse in the complex plane, draw a couple of other ellipses around it, and we can map this backwards to a picture with circles, where now the red line corresponds to the unit circle on the left. The blue ellipse, a little bit bigger, corresponds to some other circle around the origin. The green ellipse, even bigger, corresponds to some other circle. And now we're in business where we can apply Hadamard's three circles theorem, right? So this is a basic result in complex analysis, which gives us some inequality between sort of the maximum value that your nice function of a single complex variable takes on these three circles vis-a-vis the radii of the circles. Okay, and again, you can see that this is kind of going to be exactly the sort of thing we want, because what do we want to show? We want to show that the function takes a largish value somewhere on the red line or the red circle. And that's, things work out, right? We have the maximum over the red circle on the right-hand side of this inequality. So this is obviously a cartoon. We didn't go through the details, but you work things out, sort of based on these ideas, and you end up proving the result that I claimed. Okay, so what I just told you about is we have an answer to this sort of question. You've got a power series which looks like this. We can tell you something about the minimum. We can give you a lower bound on the largest value that the power series must take somewhere over the unit interval. And now we're basically done. It's just a matter of sort of tracing back through the notation and seeing that this gives us what we want. So, oops, let me maybe go back one slide. We factored out this A2 here. We saw that power series has to be at least 1 over log squared 1 over A2. So when I multiply it back together, I get something like this. I get that the supremum over the unit interval of this quantity we're interested in is at least A2 over log squared 1 over A2. Okay, we actually know, thanks to Royan, that the supremum occurs all the way at rho equals 1. And so that tells us that the quantity we're interested in is at least this thing, which looks really like what I'd kind of claimed before. A2 over log squared 1 over A2, that's exactly this kind of phi function, our sort of discount version of Talleyrand's function, where he didn't have log squared, he just had a single log. Okay. So just to kind of finish it off, let's confirm that we really get this thing that I claimed exactly. Remember, this A2 is like the inner product of the Hermite coefficients at level 2. Well, we've got a bunch of Hermite coefficients at level 2. We've got things where we've got like 2 1s in 2 different spots, and we've got things where we've got a single 2 in 1 spot. Those are sort of the possibilities for degree 2 multivariate Hermite polynomials. But it's Gaussian space. We can rotate, we can sort of diagonalize the matrix, and we can set things up without loss of generality that all these inner products, all these terms in the inner product for either one of the fixed sets that we care about, say the K set, the only non-zero entries are on the diagonal. So all these K tilde EI plus EJs, if I is not equal to J, are 0. So that cleans up this A2 quantity nicely for us. It turns out that then, right, we only have non-zero contributions from this E1, E2, so on and so forth, or I should say 2E1, 2E2, so on and so forth. And at this point, we want to stop and say, I like this quantity. We're going to define the quote unquote convex influence, or the influence of this symmetric convex set, to be the negative of this degree 2 Hermite coefficient. And we take it to be negative just so that this influence will be positive. I'll talk a little bit more about this kind of thing in a sec. But yeah, anyway, with that definition in mind, we can sort of say with a straight face that this A2 quantity is this inner product of influence vectors. And we get this expression, which really looks very much like Talleyrand's theorem. I don't have Talleyrand's theorem on the slide, but it just looked exactly like this, where we replace symmetric convex with monotone Boolean. We replace Rn by the Boolean cube, and we replace, our cut rate function x over log squared with just x over log 1 over x. Okay, so that concludes the argument for the quantitative Gaussian correlation inequality. I guess I should mention that, yeah, this technique is fairly general. There are a bunch of cases where people proved kind of, whoops, this is supposed to say, let's just bootstrap qualitative correlation bounds. There are a bunch of places where people proved qualitative correlation bounds. Oh, 2 symmetric convex functions are non-negatively correlated, or the FKG inequality tells us that suitable functions have non-negative correlation. Often when people prove these qualitative bounds, they actually do a little bit more. They prove these qualitative bounds by establishing monotonicity of some kind of interpolation. And in all those settings, you can just kind of apply our approach and get corresponding quantitative correlation bounds out. So we have a bunch of results of that flavor, but I don't want to maybe focus in on that so much as get to the very last portion of the talk, which is the propaganda, which is where I try to convince you that this notion of convex influences is maybe there's something interesting here, that it could be worth looking at some more. So let's go through this. The first thing I want to say is, there's nothing special about sort of E1, E2, E3, and that formula that I said before. We could really think about any unit vector, any direction, over Gaussian n-dimensional space, right? So if you have a symmetric convex set and any direction, any unit vector, I think it's natural to make this definition. The influence of that direction on the convex set is just what we said before. It's this degree 2 Hermite coefficient in that direction. Okay, so kind of a natural version of what we did before, where we just replace, coordinate I by direction V. Okay. It turns out that there's an equivalent formulation of this convex influence notion in terms of dilations. So we can think about expanding our set. Pick your favorite direction. Let me make it E1. We can think about expanding our convex set by stretching it by a factor of 1 plus delta in that direction, not changing it in other directions, and looking at this ratio. So we take the difference between the Gaussian volume of the stretched set and the original set, divide by delta. So it's really like a derivative, right, with respect to this delta dilation parameter. Turns out that our notion of influence exactly corresponds to this derivative. And if you think, oh, I've seen something like this before, you have seen something like this before. It's exactly like the Russo-Margulis lemma for Boolean functions. Boolean function setting, Russo-Margulis tells us that if we have a monotone Boolean function, we can express the influence as sort of the derivative of the volume with respect to like the P parameter if we're looking at like a P-biased volume. Okay, so this is a very analogous phenomenon, but here it's in this convex Gaussian setting. We have this notion of the total convex influence. So you've got your favorite direction. We'll pick n-1 other favorite directions to form an orthogonal basis of vectors over Rn. If we just sort of look at the analog of the dilation definition, now instead of dilating along one direction and leaving the other things fixed, we'll dilate the body sort of uniformly by scaling the entire body by 1 plus delta in every direction. Okay, and if we take the corresponding derivative there, that's going to be the so-called total convex influence, and it just corresponds exactly, of course, to what we would get if we dilated the body separately in all these different directions. So we have this other sort of interpretation or formula for the total convex influence, right? It just corresponds to what I got by adding up those Hermite basis functions, 1 minus x1 squared over root 2, 1 minus x2 squared over root 2, so on and so forth. We end up with something like this. And if you look at this, you see right away, this is obviously rotationally invariant. It didn't matter that I went with E1, E2, E3. I could have gone with any collection of, I could have picked my coordinate directions any way that I want. So I think that's a nice thing about this notion of influence. It's rotationally invariant. Here's a picture, I guess, of we dilate the set, take the difference, divide as we go to 0. So it's, yeah, the purple region is like the difference in volume between the dilated set and the original set. Yeah, so okay, I'm saying a lot of words. Oh, here's like some notion of influence. A reasonable thing to ask is this a good notion of influence? Does it behave like we think an influence should behave, right? So let's kind of ask and answer a few of those questions. Well, we think of influences as non-negative. Is this quantity non-negative? We handled that by taking it to be the negative minus 1 times the Hermite coefficient. Then it turns out that it is indeed non-negative. So yeah, again, just a picture of sort of the dilation. It's not difficult to argue that if you have a symmetric convex set, the convex influence in any given direction is going to be non-negative. One way you can do this is by imagining you sort of average out all the other coordinates. That isn't going to change anything. And now instead of like a 0, 1 valued function, you've got the Gaussian volume sort of within that hyperplane. So you have like a one-dimensional real valued function. And this one-dimensional real valued function, since the original set was symmetric and convex, this one-dimensional real valued function is going to be symmetric and unimodal. It's going to be log concave. So you can think of it as like a mixture of sort of symmetric intervals. You've got this much weight on, minus 0.1 to minus 0.1, this much weight on minus 0.2 to minus 0.2, so on and so forth. And it's easy to see that as you do a dilation of an interval, it's only going to increase its volume. And our overall thing is like a mixture of these intervals. So again, the volume is only going to increase under these dilations. So this is one way to see that the convex influence, as we've defined it using this Russo-Margulis result, turns out to be non-negative. So that's good. The convex influences are non-negative. We would also like it to be the case that convex influence 0 sort of means that it's like an irrelevant coordinate or an irrelevant direction. And that also turns out to be true. So this is just a picture. We can show that if your influence is 0 in a given direction, then up to a set of measure 0, the symmetric convex set has to be a cylinder in that direction. So it's like an irrelevant, you have an irrelevant coordinate or irrelevant direction v if the convex influence in direction v is 0. So that's also something we like. It sort of seems to be behaving in an influence-like way. It's nice to have some examples. So you could say, do we have sort of, Gaussian space analogs of our favorite monotone Boolean functions, things like dictators, majority, tribes function, et cetera? And the answer is yes, we have very natural analogs for all these things. So for instance, if we think about like a Boolean dictator function, it's the simplest monotone function in the world, just outputs the value of, say, the first coordinate. This is, of course, the monotone Boolean function, which has maximal influence in direction 1, which has, if you want to have x1 or the first coordinate having the most influence, well, your function should be x1. Okay, and a natural analog in the Gaussian setting is a slab. It's more interesting in the Gaussian setting because in the Boolean setting, sort of, there's nothing you can do. It just has to be x1. In the Gaussian setting, you can make the width of the slab as wide as you want. And by choosing a suitable width of the slab, the convex set, in fact, just the set period, which has maximal influence in direction 1, turns out to be just a slab like this. It just depends on one direction or one coordinate. We could also say, I'm interested in maximizing the total influence, not the influence of any single coordinate. Well, it's well known if you want to have a monotone Boolean function, the picture on the left, which has maximal total influence, the way to do this is to take the majority function. It has influence basically root n. Each coordinate has influence about 1 over root n asymptotically. And the natural analog here in the convex Gaussian setting is to take a ball of a suitable radius such that the Gaussian volume is 1/2. Again, you'll have influence in each of the n directions being 1 over root n. The total influence will be root n, and this is maximal. This is extremal for convex influences of symmetric sets. And you can go on and come up with analogs of other functions. I probably should have made this CNF tribes, an and on top and ors on the bottom, like an intersection of these disjunctions. The tribes function is really closely analogous, if you think about it, to something like a cube in Gaussian space. You're anding together these suitable slabs, or we choose the width of the slabs carefully. The same way that each of the n coordinate variables has influence log n over n in the Boolean setting, we get that each of the directions has influence log n over n in the Gaussian setting. So we again have this kind of nice analogy. So yeah, hopefully we check this box. We feel like we do have satisfying analogs of Boolean functions, but we want more than just examples. So some of the results that we're able to show about convex influences are, again, you sort of know something about what happens in the monotone Boolean case, and you can come up with a pretty good guess and prove the guess or make some progress toward proving the guess for what happens in the Gaussian setting. So the same way we have Poincaré's inequality, saying that the total influence of a Boolean function is at least its variance, you can show the same thing is true for our notion of influence over Gaussian space. There's this famous Concolli lineal theorem saying, giving sort of a better result than the Poincaré inequality. Say if all the influences are small, we have an analogous result in our setting. If all the directional influences are small, you have a non-trivial lower bound on the total Gaussian influence. There are sharp threshold results in the Boolean setting. We have analogous results for convex sets. We can come up with something like this robust version of Kruskal-Katona that O'Donnell and Wimmer gave. One area where we weren't able to get what we want is in the Boolean setting, there's this nice theorem due to Friedgut, which says that if the total influence is small, then the function must be close to essentially depending on only a bounded number of coordinates. Feels like the same kind of thing should be true in our setting. If the total convex influence is small, the function should essentially depend on only a bounded number of coordinates. We weren't able to prove that, but we're able to prove a consequence of that. So yeah, I think in the interest of time, I'm not going to really say much about the KKL theorem. This is the statement in the Boolean case. If you just think of the function as being essentially balanced, that the fraction of inputs which satisfy the function is between 0.1 and 0.9, then if all the influences are inverse polynomially small, the total influence is at least log n. We have an analogous statement, but it's quantitatively weaker. So we would get, under similar conditions, total influence square root log n. And we'd like to strengthen this, but we don't know how to do it. Builds off of Gaussian isoperimetry and a Braskamp-Lieb type inequality. Maybe do I have 2 or 3 more minutes?
Yeah, take the time you'd like.
Okay, great, thanks. It's just a few very small handful of slides. Just to tell you something about one application, some work we were doing recently. It's sort of motivated by, I guess, like a statistics question or a data analysis type question. Imagine you're in a setting where you get a bunch of points, so n-dimensional samples. They're drawn from a distribution, and there's like two possibilities, like a null hypothesis and an alternate hypothesis. The null hypothesis is they're just Gaussian. They're straight up standard Gaussian points. Each one is independently drawn from the Gaussian. The alternate hypothesis is that they were drawn from the Gaussian, but some censoring took place, and you were only shown ones which fell into this unknown censoring set. So I have like a crude picture here. The picture of the null hypothesis is on the left, where there's no conditioning. It's just everything. And in the right, we have this like, blurry or misty censoring set. We don't know what it is, but actually all the points you got, you were only shown points which fell in this unknown censoring set. Okay, and we'd like to know how many samples do you need in order to distinguish between whether you're in the null hypothesis case or the other case. So it's hopeless to answer this question. No finite sample is enough if the censoring set can be completely arbitrary. Maybe it's like a very thin mist spread throughout space, and how can you ever tell if censoring took place or not? It's also hopeless if the volume of the censoring set can be arbitrarily close to 1, because you're essentially not doing any censoring at all then. So for simplicity in thinking about this, you should probably imagine that the unknown censoring set has volume, say 1/2, but really the important assumption is this one. It has some structure. We're going to assume that it's a symmetric convex set. In fact, we don't even need the symmetry assumption, but yeah, so I don't want to spend too long on this. There have been a range of sort of related feeling results covered in the theoretical computer science literature. So maybe these last two have the closest feeling to it. This property testing type result from a couple of years ago says, if you get random examples from the entire Gaussian distribution, and I also give you a label, I tell you whether they belong to this unknown set K, which is an arbitrary set. So you have an arbitrary subset of Rn. You get access to Gaussian samples from Rn labeled by a +1 or 0 according to whether or not they're in K, and you'd like to figure out, oh, this set was convex, or on the other hand, oh, this set was actually very far from convex. So like a property testing type formulation. That turns out to be hard. You need n to the root n samples or 2 to the root n samples. Yeah, you basically can do it with 2 to the root n samples, and you need n to the root n samples. Other related feeling problems are like computational learning formulations of this kind of problem. So I promise you the set is convex. You get, again, Gaussian random examples, and each one has a label telling you it's in the set or it's not in the set. You'd like to learn what the set is, figure out what the set is. Well, you can do it from about n to the root n samples, and it's known that you need 2 to the root n samples if you want to get, say, 99% accuracy. So problems that I think feel like this problem, you're like, oh, these seem like hard problems. The sample complexity has to be like 2 to the root n, but it turns out that for this distinguishing problem, it's much, much easier. So you can distinguish the case where there was no truncation from there was some unknown convex truncation set with just a linear number of samples, as it turns out, in a polynomial time algorithm. And kind of a key ingredient in doing this, like we build off of a first case, which is like that the set is symmetric. A key ingredient in that first case is this Poincare inequality for convex influences. So these kind of structural results about this convex influence notion, at least in this one example, turn out to be useful for maybe having some algorithmic, you can squeeze some algorithmic juice out of these results. So I think I really am out of time now. I just want to close by saying there are a number of open directions which we're interested in trying to understand more about this notion of convex influences. Again, we weren't able to prove some things we would like to prove about convex influences. I think there are other algorithmic questions which are really interesting, but that's all for future work. So that's it. Thank you.
Thanks so much, Rocco. Please, anyone with questions or comments, feel free to unmute yourself and ask.
I see something in the slides. Yeah, the slides, I'll be happy to post the slides.
Hey, Rocco.
Hey, Henry, how are you?
Good. Just down the hall, but yeah, thanks for the talk. So I guess I'm curious about this analogy between the convex influences and the Boolean case. Is it in a sense like a generalization, in the sense that, like, you can actually embed the Boolean Fourier stuff in some convex body, and then all these convex influences recover the Boolean Fourier stuff, or is it?
Yeah, that's a great. Yeah, or is it not? You're saying.
Yeah.
Yeah, great question. As far as I know, it's not a generalization. There is this phenomenon where, like, if you're looking at polynomials over Gaussian space, they kind of are a special case of polynomials over Boolean space, just because if you have like many independent +1 - 1 bits, you sum them and it behaves like a Gaussian. So sort of anything
Yeah.
that could happen in the Gaussian case could also happen by just summing bits in the Boolean case. So
Right.
we're talking about stuff with polynomials. Yeah, like sort of there are these problems, some de-randomization problems and related problems where like formally, like if you're going to do something in the Gaussian setting, it's, that's a prerequisite to doing it in the Boolean setting. You will not get the Boolean result without proving a Gaussian result. But I
Mhm.
don't know of a phenomenon like that here.
Hmm.
Yeah, I don't know of a way to sort of infer the Boolean results from what we're doing in the Gaussian case or vice versa. Yeah, it
Uh,
seems like, is it a gigantic coincidence? I don't think so.
right. Yeah.
I don't know of a
Yeah.
way to sort of make that connection.
Yeah. Interesting. Yeah. Um,
No, it's
and
good.
then maybe one follow-up question, like, is there a way, so with Boolean functions, it's like very natural to think of them as like computational objects, like, maybe you compute a Boolean function using a circuit or something. Is there something analogous for like these symmetric
Yeah,
convex sets?
great question. Great question. I've been thinking about this kind of thing. I don't know of a good analogy. I remember ranting to someone over a dinner with this at some point, and I could tell they wanted to like get out of the room because I was maybe not making any sense. You can try to come up with like a Gaussian analog of decision trees, where you imagine like maybe you look at like the value of some, so instead of like querying a variable and branching left or right, I'm thinking maybe you query a direction, a coordinate, and you
Mm-hmm.
have like infinitely many branches depending on the value of v dot x. But I think if you look at that notion for like convex sets, it ends up like general sort of adaptive decision trees collapse, I think, down to like Hunter decision trees or like subspace Hunter functions. So I don't think it's a great notion. Like the short answer is I think it's a really interesting question, but I don't know how to say interesting things about like a computational model in
Yeah,
this setting. Yeah, but I think it's a great question. I wondered
I
about this
see.
kind of thing.
Really cool. Okay, thanks.
Thanks.
Could I ask a question?
Of course, yeah.
I was wondering if you could comment on where convexity is used in your main proof.
Sorry, you mean like in the proof of the correlation inequality, the robust Gaussian correlation inequality?
The quantitative version.
Yeah, the quantitative version. I mean, we really are just building off of Ryan's theorem, right? Like we use the monotonicity of interpolation, which Ryan established as a black box. It's just not true, that monotonicity of interpolation, if you have non-convex sets. But I don't know Ryan's proof well enough, and I think one would need to be sort of talking about Ryan's proof to talk about like where it's used in what he proves. But yeah, it sort of comes in this part, in the fact that, if K and L were not convex sets, then it wouldn't be true that you have this monotonicity. It wouldn't necessarily be true. Yeah. Does
I
that?
see. Is it possible that some of your results might extend, therefore, to sets which are not convex, perhaps sets which are star-shaped about the origin, for example,
I missed the last thing you said. Sets which.
are star-shaped with respect to the origin?
Yeah, I think it's not true for star-shaped sets, because I can have like two stars where the stars kind of miss each other, right? The pointy parts miss each other, and you'd have basically no intersection, even though each star is like, think of like a clock with 180 second hands, and one clock, they're all pointing at like the even seconds of 360 degrees, and the other clock, they're all pointing at the odd seconds of like 360 degrees, right? Like there are two star-shaped sets with like volume maybe 1/2 for each of them, but there's basically no intersection, just at the origin.
I see, thank you.
I think there might be settings where like, things are true. And I guess, there are a bunch of other, sorry, where was that slide? There are a bunch of other settings where for symmetric convex functions, for instance, this monotonicity of interpolation is true. And so you can get a quantitative version, and in other settings, this kind of monotonicity holds. And so you can get quantitative versions, but yeah, I think you kind of have to look case by case to see where it works.
I have a quick question.
Sure.
So I've seen generalizations of influence over various spaces before. I think partly in pursuit of a KKL over other spaces. So I've seen there's an extension of KKL that defines influence as like when a function is non-constant in a direction, and then other versions where they look at the variance.
Right.
Yeah, you're familiar with this. I was wondering how this convex influence compares to those.
Yeah, great question. So we talk about this a little bit in the paper. I think Shibam can correct me if I'm wrong. I think that the convex influence can be small in settings where those influences would not be small. So the one is like the standard kind of what I think of as like, analysis of functions over product spaces notion, like, yeah, the expected variance along a fiber. There's this notion by like Keller, Mossel, and Sen, which is, they do like, I think, enlargement where you don't enlarge sort of or dilate the set by doing like 1 plus delta times K. They do like K plus like a box of like side length delta, which ends up giving you different results. Yeah, I think that those two other notions of influence, like the Keller-Mossel-Sen notion or the like variance along a fiber notion, they can be large in cases where our notion is small. And those are also both notions which are not rotationally invariant. So you can have like a set in Gaussian space, which has influence 1, and you rotate it, and now it has influence root n. But for our notion, the influence doesn't change under rotation. But I think basically the answer is that ours is smaller than theirs.
Got it. Thanks.
Sure. Yeah.
Could I ask a question?
Sure, of course.
Yeah, so this is maybe high level, but if I'm sold on your analogy here and I'm very excited about it and want to go further with it. So your definition of influence, instead of an indicator of a convex symmetric set, you could put in any function. Would you advise against thinking of this then as an influence, right? This second level Hermite polynomial makes sense for any function, right?
Yeah, no, good question. You could do it for any function. I think as long as your set, it doesn't have to be symmetric convex. As long as your set is convex and contains the origin, you'll have non-negativity of influences. If your set, I believe that's true. If your set is kind of more general, it may be negative, in which case, I don't know, it's still an interesting quantity, but maybe I wouldn't think of it as being influence-like if it could be negative, especially if it could be negative in coordinates where the function, yeah, I mean, it'll be 0 if you're a cylinder in that direction, but if it could be negative or 0 in a direction where the function is non-trivial, I would, could still be an interesting quantity to look at, but maybe it's not going to sort of be influence-like. It's a subjective answer to a subjective question, but.
Okay, thanks. Curious.
All right. Well, if there are no more questions, I'd like to thank Rocco again for speaking. We will hopefully be posting the video and slides on the webinar website shortly. And yeah, thanks everyone for coming.
Thanks again for the invitation. I'll send you the slides, Joe.
Yeah, that'd be great.
Sounds good. Okay, thank you.
Oh, wait, sorry. If we could just pause for a second. There's one final question in the chat, I think.
Oh, great. Yeah. Are there KKL type theorems for the other definitions of influence you mentioned? Yes, I believe there are. I know that for like the Keller-Mossel-Sen, there is a KKL type theorem. I think it's sharp. Like, I don't think it loses a square root the way ours does. But again, ours is smaller, so it's potentially harder to prove. It's not a hard proof, but yeah, the short answer is yes. Yeah.
Great. All right. Thanks, everyone.
Thanks again.
Take care.
See you, Joe.
Bye-bye.